Hello, my name is Zahra. I work at Microsoft. My background is mostly on various aspects of systems, security, compartmentalization, and this talk is about one of the projects we are doing in Azure Sphere team on secure and dynamic hardware partitioning. Heterogeneous architectures are becoming more and more popular as our applications are getting more complex, their designs, their dependencies, so our workloads are getting more complex. So that's why we see, like even on IoT and edge devices, we see this demand and support for adding multiple heterogeneous cores. For example, usually a combination of Cortex-A's, ARM Cortex-M's, and RISC-V cores that are added for domain-specific scenarios. For example, for machine learning workloads or computer vision, use cases for like balancing power consumptions and like the application scenarios in a dynamic way. And specifically for also security use cases, we see support of like separate processors for like a secure enclave style of processors for doing attestations, for doing systems measurement, monitoring, verification, or like for supporting secure debugging. So it's an exciting area. We have multiple components, multiple even security sensitive components, several trusted execution environments, several like secure enclave processors, and we also have different like systems stack, like operating systems like Linux and hypervisors, and a form of like FreeRTOS or bare metal like containers on different cores. So in our team, we are working on different aspects of systems design for such heterogeneous architectures, like with our hardware partners. For example, here you can see one of our like hardwares that we are working on, IMX8 ULP. That's it's like from IMX8 family. And this specific one is like these details and internals are not like announced by NXP. So here I'm just going to talk about high-level architectures of it and things that are publicly available. So as you can see here, we support, for example, two Cortex-A 835s, separate Cortex-M. Each of them have like separate like implementation of trust zone A, trust zone M. We also have a separate core like secure enclave edge lock that's also doing other hardware-assisted security tasks such as attestation, systems measurements, monitoring, secure debugging, things like that. So this is basically like a typical heterogeneous architecture that I want to discuss in this talk. That you can see there are lots of peripherals here, like from DMAs and GPUs and like crypto accelerators, CAM, and so these hardwares should be like shared, or depends on the use case, like from our customers, depends on that. It should be like dedicated to each of these cores and be protected. To fully utilize the underlying hardware features here, we need a proper hardware partitioning mechanism. We need a mechanism that enables application developers to have some controls over like assigning which peripherals to which core, and these should be like utilized depends on applications like use cases. So at the end, we want like developers, we want the application designers to maximize their use of hardware, so to benefit from all the hardware features that are available for them. And this cannot be possible with a fixed like partitioning, like a separated separation logic that is like cannot be changed by them. So some of the like partitioning parts can be done statically. For example, like secure world systems like stacks such as like DRAM usage, DRAM memory ranges can be partitioned statically because we don't expect a lot of change on overall layout. or some of like trust zone like GPIO or CAM interface for like crypto usage. So things like that, yeah, it's okay to be partitioned statically, and we don't expect like applications to change them a lot too. But there are other peripherals like DMAs, like GPUs. These should be like more on control of application designers. And that's what I'm gonna mostly talk about, like what changes we need to do on like operating systems, on like systems stack between like this cores, and also like the challenges we have on, for example, securely debugging this, like enabling both like flexible and secure way of controlling the hardware partitioning part here. Fortunately, hardware support, like features for partitioning memory and peripherals, also having a significant progress. This is a relatively active area. We see like features like, for example, RDCs, resource domain and controllers, for partitioning memory and peripherals on IMX families. We see like SMMUs on different hardwares. We see MPUs. We see XPPUs on like SPM, like secure partitioning management on ARM v9 boards. We also had like trust on address space controller, trust on peripheral controllers. All of these features are designed for like partitioning a part of the system. Some of them can be like cover more of the systems, for example, like XRDCs and TRDCs for like covering the whole like Cortex-M and Cortex-A like interactions. But some can be like only accessible, for example, inside the secure board, like trust zone controllers. And so they have different designs, they have different protection capabilities, and they have different like security models. Now we see that several of these features can be supported on the same device, on the same SoC. And the secure integrations of like these features based on like different threat models and like use cases, it's very challenging. Here I briefly introduce some of these hardware features that we are using for partitioning. For example, RDCs, resource domain controllers, are features that like enable access control assignments on a wide range of memories and peripherals. And like we have different versions of RDCs, like XRDCs, TRDCs, depends on like the core we support. But in a high level, this feature enables us to assign a set of like resources to like different processing domains, and we have a limited number of domains, like 8 or 16, depends on the like platform. But when you assign like access control policies on like this set of like, for example, a few set of resources on a specific domain, those resources cannot be accessed by another domain unless there is like a explicit access control policy defined. And the policy can be like different for each privilege level. So RDCs are aware of the secure world privilege layers, like secure world kernel mode, user space mode, and also the normal world like layer. So we can assign security attributes for like also logical separation of like secure world from the normal world, both memory and peripherals. RDCs are basically a combination of like multiple hardware submodules, like multiple hardware components, such as like MDAC for domain access control assignment on like every bus transaction, for like such as PAC for peripheral access control assignment, like MRCs for memory region controller, and like other components that are different. The implementation and their details are different, depends on like the underlying hardware, like which core, Cortex-M or like Cortex-A, and but in a high level description, RDCs enable us to like assign access control policies over every bus transaction and every memory region and address space regions that we want, and assign them to like a specific domains with like a specific domain IDs, and assign specific security attributes to each of them to separate, for example, secure world user space like resources from normal world or like from secure world kernel like mode. So it has like a 4-level hierarchical access control policy. So in a simplified example, for example, using RDCs, we can have like we can assign different domains for different scenarios. For our application sites, like application stack that are using like Cortex-A, we can partition the resources to, for example, trust zone specific resources would be like separated from user space like resources for application sites, such as like DMA, like DRAM, like different DRAM ranges. And at the same time, we also could partition our Cortex-M for real-time like workloads. So, for example, in Cortex-M, like edge like secure enclave resources would be would be isolated from like TZM, like trust zone Cortex-M, and like or from DMA or GPUs and like micropower like partitions. So this would be like for each of like these workloads, we can have like proper partitioning of resources. And also for the shared resources, we can assign a specific like another domain. So the shared resources could have like a specific like security policies that are more suitable for a shared environment than for like a separate environment for like applications or real-time workloads. We also have like in our hardware, we also have the support for like multiple TEs and enclaves. And so as you probably know, like TEs are used for like shielding sensitive code base, like sensitive code or data from host operating system or hypervisors that are having a like really large like code base, and we want to protect this like sensitive parts of our system inside the like trust zone or inside like a like secure enclave. So these hardware components are designed for reducing the attack vectors and reducing the TCP of the entire system. And TEs are usually like supporting different features. They're not all like supporting the same set of capabilities. For example, like for even like trust zone, there are different implementations of like trust zone. Some only like protects like memory. Some like for example, TZPC, like if enabled, this like allow us to isolate like trust zone specific peripherals. For like secure boots, because like trust zone by default it doesn't like enable it. It needs like some sort of like trust zone basically virtualized TPM kind of capability inside trust zone. Or we are using like edge like secure boot, for example, for as an alternative for like pure hardware based secure boot feature. So the features of like enclaves for attestation, for measurement, for like sealing, these are different. But that's why like if like an enclave cannot provide you like with all of these features, it's usually like better to have like several like different components and combine them together to get like a strong security features that we need for different use cases. And when we have like trust zone specific like partitioning capabilities, for example, trust zone like PC for peripheral controller, like address space controller, when these features are like together, we also have like additional capabilities for trust zone specific like hardware resources. And the integrations with like RDCs, like for trust on like Cortex-M, Cortex-A, and like the RDC like on each of the cores, the proper integrations like in a secure way, in a like effective way, it's really important. Also, especially like that we're going to have even more fine-grained partitioning features, like in with ARM v9 architecture, with like realm support and like confidential computer architecture, that we're going to have like even more partitioning capabilities, partitioning manager for like fine-grained like privilege separation inside like our secure board. When we have such a heterogeneous environment, our partitioning framework is really important to be aware of or all of the trust boundaries that we have on like underlying hardware. And that's why our like partitioning framework here, as you can see, it has like several components running on different privilege layers, from like our trust on kernel, TFA on like secure monitor mode, and the Linux kernel on normal board, and all of these components are collaborating together for getting updates on any like hardware partitioning changes, assigning security policies, and making sure that the system is all of the policies are in a stable way. And we also need like cross boundaries like collaboration for enabling secure debugging. Because like some of these partitioning policies are related to like trust on a stack, some are like related to the kernel, the U-boot. So the debugging across these privilege boundaries is a challenging task. It needs like all of these layers to collaborate with each other. Also, another important design principle for us is to be able to scale or hardware support. As I mentioned before, we're going to like see more and more like hardware security features for compartmentalization, for like isolation, and if we really want to like properly utilize this hardware, we need to design the systems to be able to scale, to maintain the stacks like in a secure way, to like have an abstractions that could be like could have different backends, different T kernel backends, different hardware drivers, and this is important for like properly using the hardware security features on or underlying hardware. On the Linux side, we have our sphere partitioning module that can be enabled with kernel config sphere partition. And this module is the first layer of our abstraction for parsing and getting all user space partitioning configs, partitioning policies from our specific like device tree overlay and the interfaces for like all range of like peripherals. This module, the main job would be like to have this unified abstraction, parse all of the required policies and configurations, and it constantly collaborating with our TE partitioning module. So it's collaborating with our TE driver for like assigning the shared memory buffers and RPCs for checking the updates on security partitioning policies, and also asking the TE for changing a specific policy. So you can see here, for example, if an application developer wants to like enable an RDC protected, like XRDC protected CAM, like crypto accelerator on their like platform, on their core, they can just use this device tree, simple device tree config, and then the partitioning framework does all the hard work for seeing if there is a conflict or like it can be enabled, and enable the whole partitioning policy. We have like the similar interface, similar abstractions for all the peripherals, available peripherals on our devices. And these are basically the devices that can be shared. And these are different from like security sensitive like resources that we already like assigned for our secure board. These are important for like security of the whole systems, for example, for trust on a stack and like interactions with or like enclave. And so, these are basically the hardware resources that can be shared, and it's okay to like to be under control of like application developers but definitely are separated from security sensitive, like resources that we already assigned to our like TE stacks and all of our security sensitive components. There are also some like hardware-based limitations, and that is causing some non-trivial challenges for like on our Linux side. For example, when we have like TZA or TZM enabled, we already have like assigned some security attributes on different domains, and that's why the Linux domain, like on the normal board, when it's running on a normal board, it cannot read or write like privilege registers from that are going to affect the other domains layout and like policy changes. And that's why we are using our trusted word, the component partitioning components, to finalize the actual configurations for assigning the policy. It has like the right access to the registers, to RDC registers. And also this is important, for example, for domain-specific fault handling, for like debugging between different domains. And also like inside our like our Linux environment, since we also having a virtualized environment for like application like virtualization, and none of like these hardware features can be actually, like for example RDCs can be virtualized. So in a power virtualized environment, we have some challenges for exposing these features to our like guest virtual machines. We are resolving most of these challenges through our trusted TE partitioning module. And this module is the one that is responsible for like finalizing the actual partitioning. So it has the different hardware backends, all of these hardware features for partitioning, like XRDCs, TRDC, all of these drivers are backend of this unified abstraction. And it's also responsible for enabling secure error handling and secure file handling between different privilege layers. So the interactions between like these components can cause some performance overhead. But we also need to do more evaluation on that based on different application scenarios. But currently it doesn't add like a large overhead. It's reasonable, and mostly the shared memory and like RPC communications, the commands for collaborating between these components are very small. So it's not like both. It's not even like a large buffer share, large data transfer, or also like the attack vectors between them. We keep the interface very narrow and small. So since we are enabling hardware partitioning on like the whole system, this is a larger scope with like lots of fine-grained memory ranges and peripherals. So proper fault handling and secure debugging between all of these like domains is challenging, especially like for example when an access control violation happens in one of the domains. It can cause like RDC faults in that domains, or it can like be cascaded and cause multiple violations on the different domains. So fortunately we have like fine-grained debug registers and debugging support for all of like all of our hardware resources that we are partitioning. But the problem is that like not all domains can access read or write, and they don't have that read or write access to other domains like debug registers. So for properly like debugging between like all these cross like boundaries, we assign it a specific like debug domain, and or TE basically partitioning module. That one is is responsible for giving this debug domain the privileges for monitoring, for reading and writing, and for handling all of partitioning specific faults, that any access control violations that are happening between like different domains. And that's why we had also some synchronization issues with our Linux kernel module. That's because the Linux domain was different from like this domain, and when you want to like get some of the like debugging registers, the context switching and the synchronization for the Linux fault handler to like switch to that domain was causing some issues, and that's why we like adding like a specific SMC calls to our TE kernel, to our TE partitioning modules, for giving the right error messages for like the full report of what's going on and which domain to pass it that to our Linux kernel for like proper debugging. So here, for example, you can see like a simple like version of our error reporting mechanism for like access violation on like one of the partitioning configurations. It says like, for example, this DDR, like this DRAM, this region has the access control violation on like domain 7, and in that address, and there are like also multiple access violations that are coming from the write access, they're coming from like non-secure board privilege mode that are tried like to have the right access, and the access causes like access policy violations on that partition. We also had like a specific limitations. We see like limitations from like OpenOCD, GDB, and for like domains because they're not designed for like supporting these modern hardware features for debugging. And we need to like also extend these features for considering like for like extending them to these hardware debugging features, and these concepts of like partitioning, the concepts of domain. So these are should be integrated to our debugging frameworks. So in this talk, I briefly described the problems in hardware partitionings on heterogeneous architectures, how it's challenging to do it securely in a more flexible and more dynamic way. And I describe our current solution, current design, and some of the challenges that we are still working on that, because it's an ongoing work. As a final point for this community, it's important for us to know that like since we are adding more and more hardware security features for peripheral isolation, for partitioning, for memory isolation, and these features are going to be integrated in one single heterogeneous architecture in one device, and it's important for our systems stack, especially our operating system, to know these concepts of domains, like to have the right abstractions for the partition resources. And without this abstraction, it's hard to enable secure and like effective ways for cross-domain collaborations, for cross-domain like debugging and attack investigation systems. This feature, this concept is still kind of missing from our systems stack, and especially from our operating system. I'd be happy to answer any questions you have, and thank you.